So first question is really, some easy marks to pick up. Say precisely the definition of the divisibility relation. So, this really, everybody should be hitting this, should be getting that. I'd like to zoom out there. Two differences notice. Everybody should be getting this well. So we just want to give a precise definition, show the notation, maybe just give a positive and a negative example would be good. So we say that, well, we say for integers A and B, that A divides B means there exists a C, another integer C and Z such that A divides B, so B is equal to AC. So that's pretty much the definition in English. I guess you could put it in more symbolically. You wouldn't have to give this as well, but you could give this instead. Symbolically, you could say for all A, B, Z, A divides B if and only if there exists a C and Z, such that B is equal to AC. That's the definition. Well, it's stating an equivalence, but it serves to give a definition to this piece of notation. A divides B. If there is no such Z, no such C, we can write A does not divide B, or A does not divide B. So some examples, we can say 3 divides 15 because 15 is equal to 5 by 3, and 2 does not divide 15 because, well, there can't be such another C because the C would have to be equal to 15 over 2, and that's not an integer. Now that's probably going a little bit over the top. I mean, really, if you had the first thing, I think I'd give full marks. But, it's always good to give a positive and a negative example as well, just to round it out. Yeah. Now, the one place where people do fall down, and I see them do it, is they get it mixed up left to right. So they have this symbol, and then they'll write a factorization to give the definition of it. But what they write down is the equation for B dividing A. Yeah. So now it is a bit frustrating because it is quite compact notation. You could almost think of it that it's B dividing A, because if you kind of think that looks like a fraction, maybe if you rotate it so it's a fraction with A on top and B on the bottom, then you'd get the wrong idea that B is dividing A. It's not, it's A is dividing B. So if you're prone to making those kind of errors, flipping things or muddling things up like that, misremembering them or that, just be conscious of that and come up with a way to really cement it into your mind. Okay. Okay, part B then is to give a related proof. Part B says, use your definition from part A to prove that for all ABC, if A divides B and A divides C, then A divides NB plus NC for all of them. So this is the divisibility of linear combinations result, which we use all over the place, even without thinking, once we get past this initial material. So we let AB being Z, and assume and let ABC being Z, and we're assuming A divides B and A divides C. you let M and N, B and Z, and we want to reach a conclusion. We want to reach a conclusion that C divides MA plus NB. So we want to get to that conclusion by using the definition, showing the detailed step-by-step proof of how we get there. Well, you could say that A divides B and A divides C means there exist these other two integers, alpha and beta. Yeah. With special properties such that B is alpha times A and C is beta times A. Once you've done that, it kind of falls out into your lap because we just examine this number, MA plus NB. By substitution, we can now write it as M. Sorry, keep mixing. A is dividing B and A is dividing C. So MB plus NC. Sorry, excuse me. I mixed that up. NB plus NC. MB plus NC then is going to be M alpha A.
Wouldn't you have an A as well in the last step? A divides, not C divides. In the final statement.
Yeah. Thank you. M alpha A plus NC, so N beta A. And well, it's just a matter of factorizing A. So we factorized out the A, and then that implies that A divides this number just by reference back to the definition. Okay, so it's quite straightforward at the end of the day, but you do, in order to give a nice readable proof, yeah, you got to get all the variables playing the right roles, but make clear what it is you're assuming, make clear what the range of applicability of it is, holds for every triple of integers, make clear what the assumptions are, make clear what the conclusion is, and then justify each step. I mean, if you really want to go over the top, means by definition, there exists alpha and beta. But I mean, you've just given the definition in part A, so I would have stuck full marks or something like that. Yeah, state carefully any results about the. Oh no, sorry, that's impressive. So is that okay? Any related questions to that? Spark any associated questions in people's minds? Or? No? Okay. I mean, I haven't gone all the way through the course. I hope when we return into this early stuff that, hopefully some of it seems quite doable. I should hope. Okay, part C. So part C is this crucial result about prime numbers. Euclid's lemma. So you're given the statement of it. This is for every AB in the integers and every prime P divides AP, P divides A times B, then P divides A or P divides B. And it says, prove this lemma using the concepts of divisibility, greatest common divisor, and linear combinations. State carefully any results about these that you use. So the point about those kinds of instructions is, okay, so it's giving you a bit of a guidance, prompting you a little bit about what the ingredients of the proof are going to be. It's asking you to state the principles that you're using very clearly, but it's not expecting you to go and prove all of those principles you're calling upon from the ground up. Okay, as long as you state them clearly, then you can use them. So, okay. So Euclid's lemma. So this is same for all A, B, and C, for all A, B, and Z, and primes P, Z. And P divides AB implies P divides A or P divides B. Sometimes people, when they're laying out these proofs, they'll state any of the principles that they're going to be using at the top, and then give the proof below, and then which refers back to those. Or that might be a good approach sometimes. Or just lay out the proof and just as you need them, state each principle clearly that you're calling. Now there was. If you don't remember how it's proved, or you're unfamiliar with it, you can feel a little stuck at the start, with how to get started, and it's not immediately obvious. Clearly, we should assume P divides AB, and we know that means i.e. there exists a lambda Z such that AB is equal to lambda times P. Okay, fair enough. That's something we could do without thinking. We're asked to prove an implication, so the easiest thing to do will be to give a direct proof. So we assume the condition part, unravel that assumption. What does it actually mean? It means there exists this lambda. Okay, now the reason it feels a little bit hard to get a hold of is the conclusion we're going for is a kind of compound conclusion with an or statement. So it's this or that. It's not as if you just got one clear atomistic thing to prove, which you then work towards and try and capture it, so to speak. It's a little bit slippy. Because am I trying to prove that P divides B? Not exactly. Am I trying to prove P divides A? Not exactly. I'm trying to prove one of them must be true. So it's a little bit slippery to get a hold of. So you have to remember, the way to make progress with this is you need to arm yourself with an extra assumption. The extra assumption is that one of these fails. If armed with that extra assumption that one of these divisibility statements is false, if you can then prove that the other one must hold, that, in effect, is a proof of this or that. Okay. So we can say it could be that P divides A. In which case, there's nothing more to prove. Okay. If you know P divides A, you don't have to do any more argument to make the statement P divides A or P divides B. Okay. Because you know P divides A. It's in the other case where there's work to be done. Yeah.
Should we not say without loss of generality, because we could have picked A, B, couldn't we?
Well, I don't think we need that statement here. As long as
We could have said, well,
yeah,
P divides B.
yeah, for sure. Yeah, you could have, yeah. But that's just two different ways you could do the proof. And
both ways in theory. If you didn't say that, so sure.
No, because they're just two potential routes to the same goal. We're going to go down one route. The phrase "without loss of generality" is more where
Like an arbitrary choice, which doesn't impact the proof.
Yeah, an arbitrary choice that doesn't. So W log. So sometimes people write this, right? So this means without loss of generality. Now, let's suppose you were in the middle of some argument. Okay? just to give an example of where we would use this phrase. If you're in the middle of some argument and in the middle of the argument, you were dealing with the number n, which had a prime factorization. So n is a product of these primes. What you could say then is, you could say without loss of generality, you could assume that P1 was the smallest one. Okay. In all these primes, we could assume.
You're just saying, well, there must be a least, so we can pick whatever we want. And
Yeah.
just say that it's the least.
Yeah.
It doesn't matter which one we pick.
Yeah. Now we're not saying that in every factorization where you multiply primes together, the smallest one is always on the left. But without loss of generality, you can make it be the smallest one. So if P1 was not the smallest one, you could easily fix that by wherever the smallest one is, just picking it up and relabeling things and putting that down in front. Okay. So it's not really, it looks like you're making an additional assumption, which means your argument mightn't be true in all cases because you've given yourself an extra assumption. Yeah. But it's not really, it's still the general case, because if P1 was not the smallest one, you could simply relabel them to make P1 be the smallest one. Okay. So you're not really, assuming anything extra. But what you're avoiding is, if you wanted to be like super pedantic, you would say, well, really, you'd need n different cases here. Case 1 is P1 is the smallest one. Case 2 is P2 is the smallest one. Yada, yada, yada. And then you need a final case that PM is the smallest one. And if you're being super pedantic, you'd say you'd need all these, your argument would have to branch here. But no, you can deal with it. They're all essentially the same because multiplication is commutative. So you could say, no, without loss of generality, I can say that this one is the smallest one, and then I'll continue my argument from there, right? Whereas you couldn't say without loss of generality, assume P1 is bigger than 5.
So it's like the same. So it's like the fundamental theorem thing where we say, oh, well, we want this to equal this, so we just label it like that.
Yeah. Where we had two of these equal to each other. We said without loss of generality, assume that the two first ones are equal or something. Yeah.
But would we not, is this not like a case where we say, well, I'm relabeling A to B or relabeling B to A? Or...
Well, I don't think it is, no. Because it's not like we need two versions of this argument. Just the one version will do. Because if it's true that P divides A, there's nothing more to prove. On the other hand, we assume that P does not divide A.
Yeah. Well, that's an arbitrary decision at the start, isn't it?
Well, it's not. If I hadn't have said this statement,
you could have said P divides B, in which case we've got nothing to prove, else P doesn't divide B.
Yeah.
And it goes well along the same lines, but it's not arbitrary choice at the start.
Yeah, it is an arbitrary choice, but you don't have to address both choices.
Right. Okay, so it doesn't matter then. So that's why you don't need to use that statement.
Yeah. It's just like you're coming to a fork in the road, but both roads lead to the shops.
Right.
So you don't have to go down both roads. You just go down one of them.
Yeah.
Right. Whereas in something like this, you're super pedantic. Yeah. I mean, you don't know that P1 is the smallest one. One of them is the smallest. You don't know it's P1. So strictly speaking, you'd need n different arguments here. But they're all essentially the same. If you just hypothetically examine this first and move the smallest one to the front, then you can assume that P1 is the smallest one. Yeah. Okay. So we give ourselves this extra assumption. Now, what does that imply? What do we get?
P doesn't appear in the prime factorization. Yeah. And therefore, if AB is a multiple of B, it must be the prime factorization. B, therefore P divides B.
Yeah. That's correct. The only thing I'd say about it is that it's not in agreement with the directions in the question, strictly speaking. Because the question says, use the concepts of divisibility, greatest common divisor, and linear combinations. So what you're appealing to there is the fundamental theorem of arithmetic. Everything factorizes uniquely into primes. Except that argument isn't really in keeping with the spirit of the unit, because how did we prove the fundamental theorem of arithmetic? A key crucial ingredient was this, you see. So
It would be like a circular argument.
yeah. So if you wanted to break down your reasoning there, you say, well, you're using reasoning that needed this to prove it. So it's a little bit unsatisfactory. The reasoning, I mean, the idea is not incorrect. Once you know about prime factorizations and you know that they're unique, then you can build arguments based on whether or not a prime is present in the factorization or not. Yeah, for sure. But it doesn't ring true in this case. So coming back to the question, the greatest common divisor, we have to mention that. Can we see anything to do with the greatest common divisor here?
The GCD of P and A equals 1.
Yeah, the GCD of P and A is 1, right? I mean, what could the GCD of P and A be? It's extremely limited. See, the fact that P is a prime number. A could be any integer at all, but P is a prime number.
It's always P or 1.
Yeah, so the only options for this in any event is P or 1. But this tells us that it's not P. So therefore you know it's 1. Since P is prime, the only possible values, possible GCDs, are 1 and P. But P does not divide A, as we see. Okay, so that says that the GCD of P and A is 1. And there we've referenced the definition of a prime number. Since P is a prime, the only possible divisors are 1 and P. And the conclusion we draw from that then is we make use of the fact that GCDs can always be written as linear combinations of the two numbers. Okay, so this means that there exists an M and N, coefficients M and N, satisfying MP plus NA equals 1. Okay, so GCDs can always be written as a linear combination of the inputs. Okay, this is Visu's identity. Okay, so we're justifying the steps in our argument with reference to results from the course. Okay. Now, what we're gunning for at this point in the argument, what we're trying to get to is the fact that P divides B. Okay, because we're salvaging the conclusion statement, which is this or that, in the case that we know this is false. The first one is false. The first one is false. To rescue the conclusion statement, we must be able to show that this one is true. P divides B. Are we nearly there? What do we do?
No. Make a switcheroo with M&N.
Make a what?
Switcheroo.
Switcheroo with M&N? Is that the best? By doing?
Well, we know that P.
Okay. What we know is that AB is some integer lambda times P. We know that.
Oh, yeah, we times it by P. B.
B.
Yeah.
Yeah. Multiply both sides by B. That was the okay.
Not switcheroo.
Not a switcheroo, no. Multiply both sides by B. So you got BNP plus BNA plus B. And the point is now the left-hand side is now a linear combination of P's, because there's a factor of P here, and within the AB, there's a factor of got BNP plus N. So AB is lambda P. So N lambda P, i.e. B equals Bn plus N lambda times P. Therefore, P divides P. Okay, because we've shown a complementary divisor. If you want to be super pedantic, you could say that that's an integer. It's clear it's an integer because all the ingredients B, M, N, lambda, if you look above, they were all came to us as integers. So these two cases, P dividing A, P not dividing A, they cover all eventualities, but cover every possible world. P divides A, P does not divide A. And in both cases, the conclusion statement is true. P divides A or P divides B. The second case, because P divides B. In the first case, because P divides A. Okay. So in both cases, P dividing A and P not dividing A, the disjunction, if you want to show off, and P divides A or P divides B is true. Disjunction is the fancy name for an OR statement. Fancy name for an AND statement is? Conjunction. Yeah, conjunctions and disjunctions. But and an OR, obviously. Everyday talk. Is that okay? Any?
We've done it twice. If I said, you know that P divides AB, because P definitely divides B, and then use our previous result of linear combination.
Oh, yeah, yeah.
That way as well.
Yeah. So, So actually, yeah. So that's more efficient. What I've done here is I've slightly, given that I've just proved, no, you're right. Given that we just went to the trouble in part B of proving this result about divisibility of linear combinations, see here I was kind of repeating that explanation. So kind of here, you could have shortcutted. Could have done a shortcut from, say here, you could have gone straight to the conclusion here by part B. That's your point?
Yeah.
By part B, since we know P divides BNP and P divides AB. Or P divides P, P divides P, and P divides AB, and so this is a linear combination of P and AB. Therefore, straight away, P divides B. So slightly went over it again, the argument that was in the proof of part B, which I didn't use. Okay, any related questions or? Euclid's lemma is if you're tracing like the development of initial number theory, Euclid's lemma is central, and it really is it's the characteristic property of a prime number. And indeed, some people kind of take it as the definition of a prime number. Prime numbers are the only numbers that the simplification is always true for. The only number is different from 1 and minus 1. This is always true. Okay. So the last part is another kind of bookwork result in a way, but it's related to this issue of Fermat primes. So part D is to prove that 2 to the n plus 1 is prime if and only if n is a power of 2.
I think that it's just one way, just a normal implication.
Yes, indeed. dealing with. No, so I've got, what am I doing? It's scatterbrain. 2 to the n. 2 to the n plus 1 is prime implies n is 2 to the n. So the only way you would hope to get a prime out of this, you at least have to have that the exponent is power of 2. Some integer n greater than or equal to 0. Yeah, it wouldn't be if. Okay. Now the hint is to prove the contrapositive. Now the contrapositive statement, or the contrapositive of an implication like this, is the implication in the other direction amongst the negations of the two individual statements. So it says if n is not equal to 2 to the m for any m, but this implies that 2 to the n plus 1 is not prime. So we'll prove this contrapositive statement, which is logically equivalent to the original. It's good to make that point, that you know what, like you understand why this is a legitimate way to proceed. Logically equivalent. So if this statement is true, so is this one. And vice versa. If this statement is false, so is this one. And it turns out this is the way that the argument kind of naturally falls out, is to give a direct, straightforward, direct proof of this. So you assume the thing on the right, on the left, and then argue for the thing. Okay. So we assume n is not equal to 2 to the m for any m. Now that looks kind of a bit vague and nebulous, but what it means is just n is not a power of 2. So n must look like a typical integer. So i.e. we can say that n is 2 to the m times r for some integer m. I mean, a typical n, well, it could have some 2's in it, but there is another factor r which is odd and bigger than or equal to 3. Some integer r bigger than or equal to 3. Or I should say some odd r. Odd integer r bigger than or equal to 3. If it didn't have an odd factor in it, that means it would be a power of 2, okay? Because if it didn't have any odd factor, it means it had no prime factors apart from 2. So it would be a power of 2. We're assuming that it's not. Okay, and then we're going to show, so how do you show that something is not prime? You have to exhibit a factorization of it. Okay? So that's the way to prove that something isn't prime. Okay? Show that there exists a factorization for it. So we consider 2n plus 1 here and find a factorization for it. Look at your 2n plus 1. Well, having gone to the trouble of setting up your n like this, the thing to do to just be to substitute. So you've got 2 to the 2 to the n times r plus 1. And then you can work on this. First of all, be careful when you're doing powers and so on. If there's a product of factors in the exponent, you can factorize it out like that, but then you're looking at this power of this power. Okay. And well, there is a little bit of a trick in a way to get this to work, and that's to rewrite this as a difference of rth powers. Okay, r is an odd number, so this plus 1 we can rather acutely write as minus 1 to the power r. And normally you wouldn't do that. Take something simple like plus 1 and write it as minus 1 to some unknown odd power. But it is the thing to do here because now we can make use of the fact that we've got a difference of rth powers. Okay. That can be written as 2 to the 2 to the n minus 1 times a sum, which is going to go from j from 0 to r. And what's it going to be? It's going to be 2 to the 2 to the n r minus 1 minus j minus 1 to the j. Okay, where the hell is that coming from? So that's an example of just a factorization result, which is an instance of the polynomial factorization which is if you've got a to the r minus b to the r, it's always a minus b times the sum from j equals 0 to r, a to the r minus 1 minus j, b to the j. Okay, so we're making use of standard polynomial factorization result. Now, okay, so this what you've got here at least looks like a factorization of your 2 to the n plus 1. It deserves maybe just a little thing or two to say about it, is to just make sure or just fully justify to the reader that it's a non-trivial factorization. So remember, we're trying to show this is not prime. Now, trivially, whatever the number is, you can always write it as 1 times itself. So you just need to do something to rule out the possibility that this factorization could just be a very complicated way of writing this as 1 times itself. Now, it surely isn't, but just hit that nail on the head. Well, we can say clearly the first factor, you can just focus on the first factor. First factor 2 to the 2 to the n plus 1, because it's minus 1. We can say that this is strictly bigger than 1 since n is greater than or equal to 0. I mean, the smallest it could be is when n is 0, but then it's 2 to the 0, so it's exponent 1, so it's 2 to the 1 plus 1. So it's at least 3, in fact. Okay? So it's certainly strictly bigger than 1. Or, say it's greater than or equal to 3. Which is strictly bigger than 1. And 2 to the 2 to the m plus 1 is strictly less than 2 to the 2 to the m to the r plus 1, since we know r is strictly bigger than Why is R strictly bigger than 1? Because R was an odd number, a non-trivial odd number. So this first factor is a genuine non-trivial factor because it's bigger than 1 and it's less than the number it's factorized. Okay. So 2 to the 2 to the m plus 1 is a genuine factor. So 2 to the n plus 1 is not prime. So that's the proof of the contrapositive. But if n was not a power of 2, then 2 to the n plus 1 is not prime. It can't be prime because it factorizes like this. These are certainly integers. Everything here is integers. Certainly integers, and the first factor is non-trivial. Yeah, so it's 5 marks going for that. So something equivalent to that, I think, would get 5 marks. Okay, the main two things going here is just organizing the logic of doing the contrapositive and getting this result written down correctly. If you were struggling to, maybe because of time or whatever, that you couldn't quite exactly remember the structure of this, I mean, it would be acceptable. You could state here, this difference of R powers, it always has a factor of A minus B. If you, in the heat of the moment, if you couldn't quite capture or remember this clearly, you could always say, well, I kind of know that a difference of R powers is always divisible by the difference. You could at least state that, and you might maybe lose a mark or two, but you'd be able to finish the argument based on that result. I think for full marks, I think you'd want to be able to exactly quote this, get the factorization correct. Okay, so that was question 1. Leave it there. Yes, I've got the tutorials tomorrow, don't I? So yeah, I'll see that. We'll do some more of this stuff. Or do I have them? No, I don't. No, this is an odd week, isn't it? Week 11. I might turn up at the tutorials because Steve, there's a chance one of the other staff members might be off and we have to move around, so John might have to move to do that. Oh no, yeah. I'll definitely see you tomorrow at the lecture, won't I? Yeah, definitely tomorrow. So we'll do some more of this tomorrow.